If you studied quantum mechanics and found the math confusing, you are not alone. You're typically giving a lot of new math without context, and sometimes even the wrong context. So for example, you're told that you need to use complex vector spaces, and you may think that the difficulty comes from the fact that the spaces are complex. And that's not true. The difficulty in quantum mechanics on the math side lies that really the physics is not in the vector space, it's in the projective space, and probably you never even heard what a projective space is. So in this video we're going to see all these details so that you have at least seen them once. We're going to start looking at the real projective spaces so that you can start understanding how projective spaces work and get a feel to it. Then we'll move to the complex side and we're going to look at the difference between real and complex vector spaces, including the geometrical meaning of the inner product, which you probably haven't seen for complex spaces. And then we're going to see how the physics works in terms of vector spaces and projective spaces and how it all ties together. So this is a lot of stuff, so let's get started. So let's say H is our Hilbert space, our vector space, and psi is a vector in our vector space. Now this psi will represent a state, but if we multiply this psi by a constant, we are still the resulting vector still represents the same state. So for example, if the constant is a phase, well, phases, absolute phases in quantum mechanics don't matter, and therefore it's the same state. And if we multiply by a real number, we rescale the vector, then again, we care about normalized vectors in quantum mechanics, and therefore it really still represents the same state. So the idea is that if we take a vector and multiply by an arbitrary constant, that whole complex plane always represents the same state. And so states are not really presented one by a vector, but they're represented by one-dimensional subspaces. These are called rays in the Hilbert space, which you will see is also a more confusing terminology. So really the geometry that we're interested in the physics of quantum mechanics, we're not really interested in the geometry of the vector in the vector space. We're really interested in the geometry of these one-dimensional subspaces because those are the things that represent states physically. And the space that is the collection of these all one-dimensional subspaces together with geometry is called the projective space. And so that's really what we need to look at to get a really good idea of how the mathematics of quantum mechanics works. So what we're going to do is first, as I said, we're going to understand real projective spaces, and so that you get a good sense, and then we'll understand how complex projective spaces work. Okay, so how do they work in the real space? So suppose that we get a two-dimensional real vector space, right? So it's a plane with our x and y. What is a one-dimensional subspace? Well, it's a line that passes through the origin because each point is going to be a vector, and then you can multiply arbitrarily by a real number, and that's going to give you all the vectors that lie on the same line that crosses the origin. So the real projective line is really the set of all the lines that pass through the origin. It's a little bit confusing because this is called lines and these are also called line, but yes. One-dimensional subspaces are also called rays, but again, note the terminology is confusing because typically a ray, it's a half line that starts with the origin and goes out. In this context, the ray are the one-dimensional subspaces and it's a whole line that passes through the origin. So again, this is another point of confusion. So how do we construct it and how we can think about this projective space and why is it called projective? Okay, so consider this line, which is the constant line at y equals 1. If you take any point on the line, you're going to have you can take this point and connect it to the origin, and you're going to get a line that passes through the origin, a one-dimensional subspace. So for each point on the line, you have a one-dimensional subspace, which you can get by taking the point x1 of coordinate x and 1, and then multiplying with all the possible lambdas. So that is going to give you the whole this whole set of vectors, which represents the whole line. So again, for each point here, you have a line. And it's called a projective space because if you imagine that this is the screen of, let's say, a painting, and this is you looking around, what you're gonna do is, if you see something along this direction, you are gonna draw it here. If you see something along this direction, you're gonna draw it here. So whatever you see in this space gets projected on your canvas, and you get, the sort of the idea of perspective and stuff like that that people had discovered in the Renaissance, where they, when they had to paint and do sculptures and so on. So this is why it's called projective space, because that's essentially what you're doing. Now, instead of thinking about the point on this line, you can also think about the point on this semicircle. And again, for each point on the semicircle, you're going to have one line that connects that point to the origin. And again, instead of thinking about the point x and 1, you can think of this as sine theta, cosine theta, where theta is this angle from the top here. And you're going to have a one-to-one correspondence between this rays and this rays because they're the same rays. Now, what is peculiar, if you imagine that we start here as x equals 0 and we go and go, this line is going to come down, come down, come down. And then at the limit that we are at infinity, this line is going to be parallel, right? So the line that is the x-axis represents the point at infinity at on the y equals 1 axis. And then what happens, of course, if we keep rotating in this direction, this line is going to intersect on the other side. So the point will go to infinity, will come back from infinity, from minus infinity, and come back and come back here, right? So if we imagine that we have one line for each point on this semicircle, when we are parallel, these 2 points actually represent the same line. So topologically, we can stitch this point to this point because they represent the same point. And when we end up is this circle that is the real projective line. So yes, confusingly enough, the real projective line is a circle. A real projective line really means one-dimensional. And so this is what you get. And so the top point here will correspond to this line, to the vertical line that intersect at y equals 0, at x equals 0, and where theta is 0, so we start here. Then we start increasing the angle theta, and we're going to go at 45 degree where x is 1, so this 45-degree line will represent this point. Then we'll keep going until we reach infinity on the y equals 1 line, and we're going to get pi half for 90 degrees here, and that is going to be the same as minus infinity and minus pi halves. And then we continue, we come back from here, we get the 45-degree lines on this side, and then we can go back to 0. Right? So for each point of this line, we have a line that passes through the origin, and we can rotate here, and we're gonna rotate here. Note here again that a full rotation here, right? A half rotation here corresponds to a full rotation here. So we'll see that that's gonna come over and over. Okay, so this is how it works for the real projective line. It's not that difficult. So let's see how it works if we increase the dimension and we go and look at the real projective plane. So again, similarly, we take the plane that is at z equal 1. And now for each point on the plane, we are going to be able to connect it to the origin, and we're going to get a one-dimensional subspace, which is a line. And so that's going to correspond to one point in our projective plane. Now, again, we could go imagine to pick a direction and go to infinity like this, and we're going to get in the same way, the line is going to become parallel, and then we'll start coming from the other side, and so we're going to come at infinity from the other direction. And so what is different here is that we have multiple directions that we can go at infinity, one direction for each of the x, y plane. Note again that instead of looking at the points on the plane, we can look at the point on the sphere. So we can sort of chart our lines, our one-dimensional subspaces, either by a point on x and y, or by the angles theta and phi. Now, what's different between the real projective plane and the real projective line is that now what happens is that when we stitch the points together, we have to stitch them 2 by 2, right? Because this point and this point will represent the same line on the xy plane, and so this point needs to be stitched with this point. But this point will need to be stitched with this point because this is the line that passes through the origin that will connect the two. And in doing this stitching, right, it's not just going to become a sphere, it's going to become something a lot more complicated, a lot more difficult to visualize, because this surface is not going to be orientable. Like if you heard of a Mobius strip, of a Klein bottle, this is the same thing. This surface is not orientable. And how can we see that there is this problem? Is that imagine that we have sort of an arc here, right? And we push this arc to infinity. When it's going to reappear on the other side, right, this side of the arc is going to go here, and this side of the arc is going to go here, so it will flip. And because it will flip, right, there is no orientation, like the orientation is going to be switched as you move along the curve. And so even though this is a two-dimensional surface, we're not going to be able to represent it in three-dimensional space without making some fake intersections that are not really there to begin with. So to give you a little bit of context, right? If you've heard of a Mobius strip, this is how it works. You have a square, and you stitch this side to this side, but you don't stitch them in the same direction. You stitch them with a twist, and then that's how you construct a Mobius strip. A Klein bottle, the way that you stitch it and you get it is by stitching also the other side, right? But the other side you stitch along the same direction. So if you stitched only those two vertical sides together, you would basically have a cylinder. And then what happens is that, as you see, this cylinder, it does not come from the other side, but comes from the inside. And that's what makes the shape not orientable, right? You come from the inside, and then you keep going on the outside, and then suddenly you find yourself on the inside. Something even more complicated happens with the real projective plane, because in the real projective plane you're stitching the sides in opposite direction in the same way that you were stitching in the opposite direction on the top. And you can already imagine, if you try to twist and do these things, it's horribly complicated to do. And you can see right here that you can see that you have a circle, right? And you're stitching sort of opposites point to each other. And so really this is the same construction as the real projective space that we were looking before. So the moral of the story is that projective spaces become really, really complicated to visualize, even for real spaces. And this is basically the source of a lot of problems, a lot of weirdness in quantum mechanics, because the geometry of these spaces is really complicated, and that's where it comes from. Now we have to go from real to complex, and again I want to show you exactly what happens and what's the difference between a real vector space and a complex vector space, because you probably have never seen it. I wasn't told very well, and I had to reconstruct a lot of information by myself. So here it goes. So imagine that we have a real space that it's 2n dimension, right? So in this case it's 4-dimensional. So we have 4 independent components, 4 orthogonal directions, and we're going to have an inner product on this space where we take 2 vectors, and the vector product, the scalar product, is going to give us the norm of the 2 vectors multiplied by the cosine of the angle of the 2 directions that are represented by the 2 vectors. Now note that each direction is independent. For example, we can rotate any direction on top of any direction however we want. We can rotate just 1 on 3 without a problem. We can rotate 1 on 3, 3 on 2, and 2 on 1. So we can make a rotation in this way. And again, there is no problem. We can rotate whatever we want on whatever we want, because any direction is disjoint from any other direction. And the inner product, the scalar product, is defines one angle and only one angle between two vectors, right? So this is how it works. Very simple. Each direction is its own direction. Now, if we look at, if we turn this into a complex space by essentially we have to pair directions together in a single complex plane. So now this direction is no longer any direction, it's the corresponding imaginary direction related to the component x1, right? So what we're doing is really stitching together directions to form planes, and the complex vector space knows about these planes, and in fact the inner product will know about those planes. So if we take two vectors, right, what happens is that their inner product is given by the norm of the two vectors, the cosine of the angle between the two planes on which those two vectors live, and the phase is the rotation that you have to apply within one of these planes to go from one vector to the other, right? So the point is that directions are bundled into planes. So really the geometry is about this complex plane. It's not about the single direction. You have two angles that the geometry is defining. There are two separate angles. One is essentially the angle of rotation between a plane to another plane, and then it's another angle of rotation that is within the plane, and those two are two different things. And this also tells you that you can't rotate any direction in any direction, because what you can rotate is only plane along planes. So for example, we can rotate x1 into its imaginary component, make a rotation between the x1 direction, but we can't rotate just the real part of x1 onto the real part of x2. Like that rotation we can't do, because once we rotate this direction on this direction, we are also going to have to rotate the imaginary part with the imaginary part. Right? So these directions are not distinct anymore, they are bundled together, and the geometry knows about that link. Okay, so to put it in perspective, we have real spaces on one side, complex spaces on the other side. In the real space, the ray is the real line that passes through the origin. In the complex space, the ray is a complex plane that passes through the origin. They work the same, but there is again this higher dimensionality. And if we look at what happens to the inner product when we go to the projective space, so what happens to the geometry, in the real space we saw that the norm, right, didn't matter, because the whole line gets collapsed to a point, so it doesn't really matter the size of the vectors, right? It just matters the direction of the vector, and therefore the cosine of the angle that identifies the direction, that's something that is retained in the projective space. So you lose the norm, but you keep the angle. In the complex space, something similar is gonna happen. You're gonna lose the norm, because again, the whole complex plane becomes a point. You are gonna retain the angles between the different complex planes, but you are gonna lose the rotation along one plane, because again the whole plane becomes a point, so whether you're rotating, you're still gonna get the same point, right? And so this is where the phase doesn't matter in quantum mechanics, the norm doesn't matter, and so what doesn't matter is this angle between the complex plane. And so this tells you a little bit more precisely what's happening to the geometry and how that works. So let's now try and construct the complex projective line, which again is confusing, because you're saying a line, you're going to think of one dimension, but it's one dimension in the complex plane, so the complex line is actually a surface for in normal space. Now, this would be very hard to construct, because if we have a two-dimensional complex vector space, we already have 4 components. 4 components would be a 4-dimensional space that we have to study, and that would be very hard to visualize. But we can do a trick. So since we have a complex arbitrary number that we can always multiply here, we can use the arbitrariness of the phase here to make the d component, the imaginary component of the second component, 0. right? So we can, whatever numbers that we have here, we can multiply by a phase and make, rotate this D into C and make it a zero. Now, of course, we can do this if and only if C and D are different than zero, because otherwise we couldn't do that rotation, and so we still have an arbitrary complex number. But if we do this, what happens is that we reduce this problem in 3 dimensions. Now, the only thing that we can do, since we used the arbitrariness of the phase, we just have the multiplication by a real number. And so we have sort of reduced this problem as to one that we have seen before. Now we're looking at lines, because now this is a real arbitrary number, not a complex arbitrary number. We're looking at lines in 3-dimensional space, which is something that we can do geometrically, and we can understand how it works. So similarly as before, we take the plane at C equal 1. So now this C, remember, is the real part of the second component. And then we're going to have A and B as the other two directions, which are the real and the imaginary components of the first component. And again, if we take any point on the plane, we are going to get one line that passes through the origin, and that will correspond to a one-dimensional subspace. And again, as before, we can instead look at the hemisphere, and so for every point in the upper hemisphere, we are going to have one-dimensional subspace, right? So again, as before, for every point on the surface and any point on the hemisphere, we get one-dimensional subspace. The way that it's different, though, is now if you look at the plane at C equals 0, right? All the points that are on the equator of the sphere are on the same complex plane. So when since they are on the same complex plane, we need to stitch them all together into a single point, because they are part of the same one-dimensional subspace. So it's not like before that we have to stitch together points that are sort of at the antipodes of each other. We just stitch all the elements, all the circle to a single point, and therefore we are going to get a sphere. So the complex projective line is a two-dimensional sphere. And sometimes I feel that mathematicians like to choose the most confusing terms, but anyway, the complex projective line is a sphere. And again, geometrically, the way that we can look at it is that the top point corresponds to this vertical line, right, which is the point where both A and B are 0, and the angle is also 0. Now, if we rotate along this direction, right, we are rotating along this direction, and at some point we are going to hit the point, this point 1. If we rotate it on the other direction, on the imaginary side, then we would rotate along this direction, and we would get the point I. And the same, if we rotate it in the other direction, we would get 1. And again, once we rotate all the way down, we get the one point at infinity. So it's not really a point at infinity, it's going to be sort of a circle at infinity that represents the same subspace. And this is the sort of the point at the opposite, it's the plane at the opposite side of this. And that's it. This is how the complex projective line works in terms of the math. And now, of course, we are going to be interested in, okay, what does this mean physically? How does it map to quantum mechanics? Well, the way that it maps in quantum mechanics is that this sphere that we found, it's called the Bloch sphere, and it's the set of states for a spin 1/2 system or for a qubit, for a two-state quantum system. And so the top and the bottom point would really be a spin 1/2 system prepared in the vertical direction, either up or down, right? So you see the direction in the Bloch sphere, really in the projective space, it really represents the direction in physical space for a spin 1/2 system. And so you would have, on this side, you would have x, on this side you would have y, on this side we have the opposite x minus, and so on, right? So every direction on the Bloch sphere represents a physical direction in space. And note though that remember this bottom point represents this circle, right, on the vector space. And so a rotation of 180 degrees on this space, right, represents a 90 degrees on this space. And that's why opposite directions of spin are orthogonal in quantum mechanics, meaning that in the vector space they are orthogonal. But they're really, in the opposite direction for the Bloch sphere. And now if we look at superposition, right, what happens is that every state psi can be seen as a superposition of x plus and y minus. And you see this angle here, this cosine theta over 2, represents half the angle that you have in physical space, right? So if I wanted 180 degrees here, I would have 90 degrees here, such that the cosine would be 0 and the sine would be 1, right? So this 1/2, this factor of 1/2 is really the factor of conversion for angles when we're going from the projective space, the physical space, to the vector space. And you might have heard, for example, that spin is the double cover of the rotation group. Well, here we see exactly what happens. You see, one direction here cuts the sphere into 2 points, right? So this line really represents 2 points in the vector space, while it really represents 1 point in physical space. So this idea of the double cover really is an artifact of the representation of states inside the vector space, right? It's not something that happens physically. When we do 180 degree rotation, here we are in the opposite side, and another 180 degree rotation gives us, we go back where we start. But in here, in the vector space, that 100 degree rotation corresponds to this 90 degree rotation. And if we do another 90 degree rotation, we get here. But this represents the same line as we had before, is just flipped. So again, the main point that I'm trying to get across is that, yes, we have the vector space and we have the projective space. The physics is here, but the projective space are very hard to work with, and so we work with vector spaces because they're nicer to work with. But you have to be careful that there is this translation that is happening. And one way that we can see that the physics is here, as we said before, the projective space does not care about the norm and the phase. And we can see that the Born rule, the way that we calculate probabilities, does not care about norm and does not care about the phase. This is the general expression for the Born rule. And if you look here, we are going to get on the top side, we are going to get a norm for psi and a norm for phi and a norm for phi and a norm for psi. And again, on the bottom, we're going to get 2 norms for psi and 2 norms for phi. They're going to cancel out. And so this is not going to depend on the norm. For the phase, the phase is going to be 0 because they're same vectors. Here, since we are changing the order, the phase is going to shift. Therefore, the phase is going to cancel out. The phase does not matter. And the only thing that remains is the cosine taken twice. So we have the cosine square of the angle in the vector space. And now, if you look and use the half angle formula, this is going to be 1 plus the cosine of double the angle in the vector space over 2, but double the angle in the vector space becomes the angle in the physical space. So if, on our spin 1/2 system, if the angle is 0, the cosine is 1, so we get 1 plus 1, 2, so we get that the probability of getting the same direction is in fact 1. If we get an orthogonal direction, then the angle here is pi halves, and therefore we have 1 plus 0 over 2. So the probability of measuring something that it's 90 degrees is 1/2. And if it's on the opposite side, it's 180 degrees, this would be minus 1, so we get 0. And so the probability of measuring the opposite direction is 0. So the physics works. And again, we just have to be mindful that there is this translation going on. And I hope you can appreciate how, you can actually see the geometry much better if you look at it like this. Another thing that should be a little bit more clear is that oftentimes people say that superposition states are kind of like probability distribution, and that's not at all true. Superposition are just linear decomposition, so we're just saying, again, here, we're just saying that this vector in this direction is this vector plus this other vector. In the same way that when we have forces, we have the horizontal component and the vertical component, and there's nothing weird that the force is a linear combination of the two, right? We don't say that the diagonal force is kind of like a probability distribution of the horizontal force and the vertical force. No, it is just a different direction. In the same way, right, if we have spin up and spin down, spin right is, yes, a superposition of up and down, because in the vector space we can do that, but in the projective space, in physics, is just a different state with a different direction. So we're not really getting any probability distribution, you're just getting a different state. The thing that is a little bit confusing is that we are used to think about orthogonal direction being orthogonal in the vector space. So we compose a sort of up with left, right? That's what we typically do. But in quantum mechanics, we compose up with down. Again, because the composition happens in the vector space, but the physics is in the projective space where the angles are down. That's it. So the other important thing is that everything is a superposition of everything else. So it's not that there are states of superposition. Every state is a superposition of some basis, and every state can be a basis on which you do superposition. So we can express x plus as a superposition of z plus or z minus, or z plus as a superposition of x plus and x minus. It doesn't matter, it's just a choice of base, in the same way that for a force we would pick these two directions or these two directions to do the decomposition. It's just arbitrary. There are no more true decomposition for forces, and it's the same thing for a superposition in quantum mechanics. You can pick any base you want. To see how the superposition actually works, so that we can start understanding how the geometry works during time evolution, let's see how that works. This is the Schrödinger equation. The idea is that we have a Hamiltonian, a linear operator that we apply to a state, and this is going to be equal to the sort of the time evolution operator applied to that state. And one of the things that we can do is choose a state basis that is convenient, and we're going to choose the one that is going to have the eigenstate of the Hamiltonian, so that we basically decompose the whole motion into two independent motion. That's essentially what we're doing. And so we diagonalize this matrix, which again we imagine a two-state system. So we're going to have two energies, E0 and E1, and we are going to imagine that E0 is smaller than E1. On this side, this is sort of the instantaneous equation, is the partial differential equation, and we can also integrate it so that a psi at a time t is the psi at time 0 with a unitary time operator applied to that state. And solving this equation, that's this u of t is just going to be the exponential of ht over ih bar. And again, the eigenvalues of these are just going to be the exponential of the energy times t over h bar, right? So these are called unitary operation because they preserve the unit. All states that are norm 1, they remain norm 1. But really you should think them as rotations. You see what's happening here is that in time you're just adding a phase to each complex plane, and so you're just doing a rotation. So, for example, this is our four-dimensional real space, that is the two-dimensional complex space. So this plane here represents the eigenstate of E0, and this other plane here E represents the eigenstate E1. And so what we're seeing here is that we have a rotation from the imaginary part to the real part, like along this direction, right? Where the angle is E0 times t over h bar, right? So we're basically rotating along that plane. And something similar happens on the other complex plane, right? We are rotating again from the imaginary part to the real part. We're doing this rotation. And again, the angle is going to be given by E1 t instead of E0 t, right? So if E1 is greater than E0, you are rotating on this plane faster than you are rotating on the other plane. Any other direction, any other vector is going to be a superposition, a linear combination of a vector on this plane and a vector on this plane, right? And so you just decompose it into the two rotations. You rotate the component, and the rotated vector is the sum of the rotated components. So that's sort of geometrically how it works and why it's easy to understand. Now this is what happens in the vector space. But again, we are more interested in the projective space because that's where the physics is. So how does it work in the projective space? So again, we have our Bloch sphere here. We choose that the bottom point is going to be the eigenstate at the lowest energy, and the top point is the eigenstate of the higher energy. So what happens now is that the states are naturally ordered vertically by energy, and so every circle, like we cut horizontally, every circle is the set of states at constant energy. And the Hamiltonian evolution, the Schrödinger equation, conserves the energy. So if we're moving and we have to move on that circle, the only thing that can happen is that we're going to rotate around each circle at a constant energy level. And the amount of rotation theta on the projective space is going to be given by the difference of the angles, which is going to be given by the difference of the energy. So if the two energies are the same, there is no rotation. If the energy here is higher than the energy here, we rotate on this side. So we rotate x towards y and y towards minus x and so on. If E0 instead were higher than E1, you just rotate it in the other direction. So that's it. That's how you can visualize what's happening both in the complex vector space and in the projective space when you're doing a unitary operation when you are evolving through the Schrödinger equation. Now, the n-dimensional case is going to be more complicated, of course, but conceptually is the same thing, right? We're going to have a complex plane for each eigenvector, and there is going to be a rotation within that plane, and every other thing is just the composition of all these rotations, and we are going to have a projective space that we are not going to be able to visualize because it's going to be horribly complicated, but there are going to be some rotations there as well, and again there is going to be an ordering with energies, and things are going to be rotating inside the subspaces of equal energy. So I hope again that this gives you a little bit more of an idea of what happens geometrically, and it sort of makes you a little bit more comfortable with the math. At least it did that for me. Another thing that I want to point out here again is that superposition not only it's something that it's not a probability distribution and so on, but it's really a property of any linear system. It's not something that it's there in quantum mechanics as well. So this is from Wikipedia, which actually states it really well, is that the superposition principle states that for all linear systems, the net response caused by two or more stimuli is the sum of the responses. So if A produces response X and B produces response Y, then the input A plus B produces X plus Y. So Again, forces in some regime are going to be linear. A lot of the electromagnetism, classical electromagnetism, is linear. So it's not this mysterious thing. It's just a mathematical probability that is convenient. And the other thing that I want to stress out is that this linear properties, this linearity, is a property of the vector space, not of the projective space, because that's that's defined on the projective space. So the quantum superposition is not really a physical property because it's not a property in the projective space. It's a property of the vector space representation. And that's what makes this vector space representation so convenient that we would rather use that than the horrible mess the projective space would be. And so when we say that x plus is, square root of 2 over 2 z plus plus square root of 2 over 2 z minus, right? These coefficients are representation dependent. You could have a different representation where those coefficients are different, right? So the actual superposition is not a physical thing. The fact that we can use a vector representation and that we could write in principle superposition, of course, that's a physical thing because we're using the projective space of a complex vector space. But the actual numbers that we're putting there, those are not physical. And one nice way to see it is this sort of counter example that I created where we have a map that it's not a linear map, right? So it does not preserve the inner product, it does not preserve the structure of the vector space, but it does preserve the fact that a complex plane gets mapped to the same complex plane. So in terms of the projective space, it's what is called a collinear map because we're preserving these points in the projective space. And how does this map work? If you're interested to look at it, well, again, we have a two-state system just to make our life easier. And any state is going to be the superposition of z plus and z minus. So it's going to be given by two coefficients. And the way that we map it is we map it to other two coefficients. The first coefficient remains the same. The second coefficient is the second coefficient, but we add a phase shift that depends on both components. And the way that it's going to happen is that it actually depends on the angle that we have, that the vector has between z plus and z minus. So for example, if we map z plus, right, then we're going to have 1 and 0. And so this is going to be 1 and 0. So we're going to get z plus again. And if we're mapping z minus instead, this is going to be a 0 and 1. So this is going to be 0, this is going to be a 1. This is also going to be a 1, and this is going to be 0 plus 1, so it's going to be 1, so it's going to be 1 over 1. So we acquire a phase shift of an I, a 90 degrees phase shift. Okay, now if we do the sum, if we do the map of z plus z minus, we're going to have two coefficients here, 1 and 1. So the first one is just 1, and we just copy it here. And this one is going to be 1 here. 1 plus 1 is going to be 2, so it's going to be 1 over square root of 2. And so we acquire a phase shift here that it's I over square root of 2, so it's a smaller phase shift that we get here. And you can see that the sum of these two is not the sum of this. So it's not true that the map of the sum is the sum of the maps. Therefore, this is not a linear map. However, we can show that this map is collinear, that it's going to map complex plane to complex planes. And how we do that? Well, again, we're going to have that a complex plane is a vector psi times an arbitrary lambda constant. And so we can express psi as a superposition of z plus and z minus. And now we connect the lambda inside the components. And when we map, this lambda is going to be mapped through the components. So we have a lambda here, and a lambda for each of the components here. But note that we have a lambda square and then a square root for each terms. So we can take the lambda out, and the lambda is going to cancel out, and therefore we're just going to have lambda times c1 z plus c2 the phase shift and z minus. So effectively, this is going to be lambda times m applied to psi. So you see the lambda goes outside, right? So this means that the map of a complex one-dimensional subspace is the one-dimensional subspace of the mapped vector. Therefore, we are preserving the collinearity, and so in principle, the inner product is not preserved, right? Because there's going to be a phase shift that is going to be changed by this term, but the angle between complex plane is going to be preserved. So the Born rule is going to be preserved. The probabilities are going to be preserved. So you actually get the same physics. Right? So the linearity that we get in quantum mechanics is something that we put in, that we wanted because it's nice, it makes a nice representation, but it's not part of the physics. Okay, so let's wrap this up. The main difference in quantum mechanics is not the use of complex vector spaces, but the use of projective spaces. This is where it makes the whole apparatus feel strange, because really you have never seen a projective space anywhere else in physics, and you're probably not taught that that's what you're doing, and therefore you're sort of doing some things, but you're not really understanding what you're doing mathematically. A quantum state is not a vector in a Hilbert space, but a one-dimensional subspace, a complex plane, or array, right? It's an array in a Hilbert space. And we saw that for spin one-hand systems, we saw that angles in a Hilbert space are half the angles in the physical space, because the half sphere is stretched to a full sphere, so that 90 degrees becomes 180 degrees. And that's where all this notion of double Coverous spin and so on comes in, and that's where why 180 degrees differences in physical space become 90 degrees orthogonality in the vector space, right? So that's where you have this problem. And then the other thing that I think is important to me is that the superposition, the linearity, is a property of the vector space representation, not of the projective space, and therefore it's not fully physical. You shouldn't think of this linear superposition as really something that you're really doing the physical work completely, right? There is something about it that is physical, of course, because the representation can exist, and it's convenient for doing calculation. It's convenient also to get a sort of understanding of how the math works, but be careful in assigning too much of the physical meaning to it, because that's where you're gonna get into trouble. So that's it. I hope that that helped you a little bit to get more of a clear idea. This is all material that I had to collect from a million different places, because I had all those misconceptions as well, because I was taught similar to you. So I hope that was useful to you as much as it was useful to me.